Thank you, appreciate it. Yes, I work for Samsung, and I've been with them for a couple of months. Actually, like leading their security team in organization which is called Samsung Strategic Innovation Center. And we are mostly what we are doing building IoT ecosystem to make sure that all IoT devices can connect to our cloud and transfer data. Before that, I worked in Intuit for 7 years. But whatever I'm going to talk about today is not directly related to my work. It's not related to my recent or previous employers. And please do not confuse all opinions that will be expressed in the scope of this presentation with that of my employers. Otherwise, they might not allow me to go to this type of conferences next time. So keep us separately. I did all this research like in my free time, and it was interesting. The other like curious thing about this presentation is the title. I created it, and then I started thinking that it sounds a little bit funny, because if we are talking about perfection, there should be only one grade, right? And there could not be like 7 grades of perfection. But the reason why I have it in the title is because it's not about the concept of perfect forward secrecy, it's about implementations. And when it comes to implementation of anything in real world, we all know that there is no such thing as a perfection, so that's why I have all the 7 grades. And in addition to that, I just can say that perfection can be very individual and subjective. Everybody usually defines his own perfection, what it means for him. And I promise you that in the end of this presentation, I will provide my opinion about how perfection should look like in the world of TLS handshakes. So this is what this presentation all about. So before going further into details, let us take a quick look at definition of perfect forward secrecy. And actually, when you start browsing internet trying to find out what it is, you might find different kind of sometimes confusing definitions. I didn't like many of them until I found one which is you see on the screen. So there is like work which has been published in 1992 by Diffie, Orchard, and Wiener. And that work is called Authentication and Authenticated Key Exchanges. And the definition of a perfect forward secrecy that I found there was very good. And it matches the purpose of my presentation very well, so I'm going to use this one. So under perfect forward secrecy implementation, long-term secret key materials, compromising of long-term key materials should not lead to compromising of data that has been encrypted previous runs. This is what this definition says. And I like it. It is very simple, very clear, and right on the spot. Returning to the world of TLS and SSL, we probably need to provide more details. So usually, like when you have a SSL server and SSL termination point, you will have a private long-term key. I will call it LTK, which is stored on the server, and it's stored there for years until it's rotated. And then you have a short-lived key or session key, which is calculated by client and server in the process of establishing an SSL session, and I will call it session key. So now I think like after we are good with definition what perfect forward secrecy is, we might want to take a look at the threat that PFS protects against. So this is like a very common and popular scenario nowadays. Everybody is using Wi-Fi, of course, and moreover, people are using Wi-Fi in public places, and in public places they might have public Wi-Fi spots, and nobody cares much about who set up this Wi-Fi hotspot. They just connect, especially if it's free, if it doesn't require a password, they just connect and use it, right? And usually, like in all Wi-Fi attack scenario, you will see this vicious guy with laptop sitting somewhere in Starbucks trying to set up his hotspot and steal your traffic. But in my scenario, I don't even need this guy. What I can do, I can set up this wireless, like powerful router in densely populated area, I can install DDWRT software on it, and many Wi-Fi routers support it, and it's like really easy to do that. And on top of that, I can install TCP dump software. Again, it's very easy to install TCP dump on wireless router when you have DDWRT software installed there. I did it, it worked very well. I use it not for this scenario. I use it to, for penetration testing of mobile devices that were going to the my Wi-Fi router, and then I could see all the traffic, and I could see what was going wrong with iOS devices or Android devices. So it works, and it's relatively simple to set up. Then what you can do, you can record all that encrypted traffic. You can configure your TCP dump in such a way that you will monitor only the traffic with certain destination. For example, you want to monitor all traffic which goes to Bank of America. And after this is done, you can configure your wireless router to talk to very inexpensive cloud storage solution, like Amazon Glacier, where the price of storing data is 1 cent per gig per month. So it's very inexpensive. And you're just like accumulating this data for years. And you wait for an opportunity. And then opportunity is coming. Heart bleed, and suddenly this key got compromised. You're taking this key, you're retrieving all your data that you accumulated for a few years from Amazon Glacier. Again, price is very small, 5% per month free, 1 cent for extra. After this is done, you're using this key to decrypt all traffic, and suddenly you have all financial data, very sensitive data at your disposal. So before we go to mitigation scenarios and to see how perfect forward security works, we need to understand how traditional TLS works. So this is like a traditional TLS. It has been introduced before perfect forward secrecy. And you have two parties here, client and server. And for those who are familiar with how SSL TLS works, you probably have heard about this, all these messages like client hello and server hello. We're actually party exchanging with random numbers N and B in clear, they're not encrypted. The only thing which is encrypted here is pre-master key, which is created on the client, and it's encrypted with the server public key. So this pre-master key is encrypted, sent to the server. Then server uses its private key to decrypt pre-master secret. And after this is done, both client and server has a secret that they can use to derive real symmetric keys and to use the symmetric keys in the scope of SSL session. So this is traditional one. And of course, it's clear from this diagram that if server-side key is compromised, then all of this traffic, all these pre-master secrets can be decrypted as well, and SSL session keys will not be protected. So now let us move forward and take a look at Diffie-Hellman algorithm, which was initially created in 1976. It's almost like 40 years ago. And surprisingly, its popularity is still not that big as traditional RSA encryption. And I will tell you why in a moment. But let us take a look at these parameters which are used in the scope of TLS handshake. So this previous diagram that we just discussed has been extended with additional parameters which are related to Diffie-Hellman algorithm. So you would need to have P, which is a big prime number. You will need to have its primitive root, such as for each A coprime to P, there is K, such as J power K is congruent to A modulo P. So it's not like a very complicated math. You can find all of that on internet if you need more details. It's basically it's simple. And after like these parameters are chosen, you can easily calculate YS, which is a public key of the server. And you have formula for that GA modulo P, where A is a private key of the server. And what's important, this private key never leaves the server. It never gets transferred to the client, either in clear or encrypted. So that's why it's like really private. And whoever is trying to eavesdrop your traffic, they will not be able to uncover it. And on client, similarly, you're calculating your public key using this formula G power B modulo P. And then server and client exchange the secrets. And as a result of this calculation, this is how client calculates a shared secret, and this is how server calculates its secret. And it's equal G power AB modulo P. So the cool thing here is that this long-term key that we still have on the server is not used for cryptography. It's used for authentication purposes only. That server key exchange message is signed with the private key of the server, and the signature is verified by the client using the public key. That's all. So like it means if this private key on the server is stolen, you still cannot decrypt the traffic that has been encrypted before. So as I said, this algorithm is very old, and there is RFC 5246, which is related to implementation of this Diffie-Hellman algorithm. But unfortunately, the adoption rate was not that great, and the major reason is performance. This is a diagram that I took from Vincent Bernard SSL TLS blog, very interesting reading. I have a link, you can check it out yourself. So actually here on this picture you have two diagrams. On the bottom you have response time. So you can see that if number of transactions per second grows and around 500 transactions per second, the response time goes from 10 milliseconds to 10 seconds, which is a very significant increase, of course. This is for Diffie-Hellman. And if you look at the successful transaction rate, then you will see that number of successful transactions drops to 0 at approximately the same TPS rate. For traditional RSA, this number is 2500. So the response time starts growing at 2400. So from this graph, you can figure out that the difference in performance between traditional RSA and all the Diffie-Hellman is approximately 5 times. So what is the solution? This is a solution. It's called ECDHE. This is Diffie-Hellman with elliptic curves. With elliptic curves, it's a little bit like more complicated. You have more domain parameters. You would need to have P, which is big prime, and this P is used to define a field FP. And then you would need to have the curve itself. Curve is defined by this equation, and parameters here is alpha and beta. Finally, you would need to choose a base point or generator, as some people call it, and with an order which is big enough. Order is an interesting thing. It's a minimum number n under which a production ng is not defined, while for everything which is smaller than n, it's defined. And this order should be big enough to make sure that production of order by cofactor. Cofactor is like actually a very small number. Idealistically, it should be 1. It's best from security point of view. So there should be, this equation should be valid. Order multiplied by cofactor should be equal to the order or the order of elliptic curve group over field P. As I said, like if cofactor is 1, this is the best solution, but sometimes it can be like bigger than that. And after all these parameters are defined, it's relatively easy to calculate public keys for a client and for the server. For the server, this is just a production AG, where A is a private key. Again, private key is stored on the server. It never is sent over wire. It just stays there forever. And similarly, you can calculate client public keys and exchanges public keys, and calculate your shared secret on server as A multiplied by YC, and on client as B multiplied by YS, and it's the same as AB multiplied by G. So again, like in this scenario, compromise of long-term key is not going to lead to compromise of previously encrypted data, so that's why this algorithm is compliant with perfect forward secrecy concept. Speaking about numbers and returning to Vincent blog again, you will see that while difference in response time, this 3.1, between all the Diffie-Hellman and RSA is like 3 times. If you compare the same RSA with this one, which is optimized version of Diffie-Hellman with elliptic curves, then overhead is only 15%. So 15% is nothing. I think then all this like reasoning that we cannot use ACDHC because it's slow simply is not going to work here. So it's like a perfect, looks like a perfect candidate for implementing perfect forward secrecy. Just to summarize everything, I created a table just to understand the differences between 3 major approaches to TLS handshake. The first one is classic, and it's not compliant with PFS concept. The other two, older Diffie-Hellman and Diffie-Hellman with elliptic curves, they are PFS algorithm. They have more parameters. I separated these parameters like in 2 columns. In first column, I have public ones, and by public I mean that they are sent unencrypted over wire between client and the server. And for private ones, they are either kept on the party that generated them, either on client or server, or if they send over, like in the case with pre-master secret, they should be encrypted with LTK. So the next column is very interesting. It's talking about long-term key purposes. So in the case of classic PFS handshake, the usage of LTK is for authentication and encryption. So meaning that if it's compromised, then like all your previous traffic can be compromised as well. While for Diffie-Hellman and for ECDHE, the key is used for authentication purposes only, meaning that client can sign some messages like server exchange message, and then client can use this, server can sign it, and then client can use it to verify the identity of the server. So if he doesn't want to trust to the server, he just will stop there. If he trusts, he will proceed. So it means that like if this kind of long-term key is stolen, that the maximum that an attacker can do, he can just install this legitimate key on his malicious server and try to spoof a legitimate server to trick some clients to connect and steal their data this way, which is of course like a much smaller risk in my view, because it would be more difficult to implement. Then yet another important column, it's talking about attacks complexity. For Diffie-Hellman, either with curve or without curve, the complexity of an attack is the same as a discrete logarithm problem that Martin was talking today about it in his key presentation. And for RSA and DSA, you can actually find many papers where people are talking about how RSA keys can be compromised. It's out of scope of this presentation, but I just want to mention one fact. It's been long since RSA 1024 has been considered as not secure, and it's not recommended by anymore. So there are attacks on RSA keys that you might want to consider if you want to continue using RSA stack. And finally, speed. RSA stack is still the fastest. All the DHC is very slow, as we've seen from Vincent diagrams. And ECDHC almost as fast as classic RSA, so there is no any excuse not to use it. So with all these options in place, like 3 different methods of doing TLS handshake, we can add like 2 additional parameters, which I didn't mention before. The thing is that like in TLS world, server usually has so-called preferred ciphers, right? And they're like flags, for example, in Apache server, where you can say honor the order of ciphers. So it means that like server will try to connect in the order that have been provided in the configuration file. And yet another criteria that I want to consider, if your solution is PFS, I still want to understand if you just enabled older Diffie-Hellman ciphers or you use newer Diffie-Hellman with elliptic curves as well. So if we combine all those parameters together, we can come up with this table which actually describes the grades that I want to use in the rest of my presentation. So the first and second case, grade number 1 and 2, this is when only PFS ciphers are supported, nothing else. The difference is in the preferred cipher. It can be the faster ECDHE or older DHE. Then third and fourth cases, this is when both PFS and non-PFS ciphers are supported. But difference again is what preferred cipher is. Is it the faster cipher with curves or an older DHE? And finally, the cases 5 and 6, this is when preferred ciphers are non-PFS. But the difference is that in the grade 5, both DHC, ECDHC, and non-PFS supported. One grade 6 means that there is no support for the fast elliptic curve Diffie-Hellman ciphers. And finally, grade 7 is when PFS ciphers are not supported at all, and preferred cipher is non-PFS, obviously, because nothing is supported. If you want to, if you don't like so many grades, you can easily reduce it to 4 by combining 1 and 2, 3 and 4, and 5 and 6, right? Like security-wise, they're equivalent. But I think that performance is very important here. Because if you don't care about performance, from my experience, you're not going to implement anything. You're not going to have a buy-in from developers. They will tell you, you know, it probably is very secure, but we cannot afford a response time dropping like 5 times because of your solution. So I think you still need to take into consideration the performance when you implement your security solution. And probably we need to start thinking about adding P to CIA triad. So this is not only confidentiality, integrity, availability anymore. We need to add performance if you want to be successful in implementing of what we want to implement. Actually, like I noticed like lately that I'm spending more time on figuring out how to make it perform better than like thinking about security. So this is what I already said. And yeah, just 2 more words about this, why this preferred cipher is important. Because if client, the way how they start communication, client can send like a lot of ciphers. It can send like good ones and bad ones. And server, if like preferred cipher is not like very good, will always select the preferred one, even if client has a better cipher in the list. And so that's why you need to pay attention to preferred ciphers. So now returning to the testing, my approach probably was not very scientific. I just selected some like 10 areas of 10 industries. And to find the top companies, I just Googled them, asking Google questions like top 10 manufacturing companies or top 10 finance companies and things like that. I'm not going to disclose any name. I have this code published. If you want, you can test whatever you want. So the interesting thing was this defense industry, because it was, believe it or not, it was very difficult to find SSL-protected websites there. Everything is public. Yes, and the only way for some of them, the only way to find something which is SSL protected is to go to their like job websites. And this is where they protect the people who are applying for the job. This is the type of sites that I've tested. So I've used Python with PyY OpenSSL package. And the code is available. You can see this link on the bottom. If you want, you can play with it. So this is how it works. This is the long list of ciphers that you see on the top. This is what I'm just taking from OpenSSL using this minus cipher keys, and it's just like print everything. So basically, I'm taking everything which is supported by OpenSSL and sending it to the server, hoping that it will do its own work by selecting the preferred ciphers, the ciphers that it likes the most. Then I have yet another parameter which is called baseline ciphers. And I'm using these ones mostly to do some kind of very simple benchmarking to compare time of response time from client point of view for PFS and non-PFS ciphers. And this is a very popular ciphers. They are supported by almost everyone, so at least one of them will work in all cases. And then, of course, I have a bunch of websites that I want to test. You have host parameter here, port, name of the organization, and the last one is industry where it belongs to. And as a result of this test, an HTML page like this will be generated. And this is like real test. I did it like a few months ago. I didn't repeat it yet. Probably I should after the Spoodle attack. I think like many organizations should make some changes. So the first impression of this is that we have too much red color here, right? And red color, as you remember, this is like rate 7, meaning that no PFS cipher is supported, preferred or not PFS, so the picture is not very good, right? There is a perfect world in the middle. You may wonder what it is. It's not a real website. It's just like 3 websites that I created on my own, in my own like local environments, just to make sure that it's possible. And after I created it, I decided, okay, I have all this like traditional web browsers, the most popular ones. Let me try to connect. I try to connect, everything is working. So I'm not buying this like excuse that we don't want to move there because like it's not supported by browsers. All contemporary browsers support PFS, period. So let's just like do a little bit more analysis. So winners, internet company, infosec companies, defense and education. So it means that they have like at around 50% of their websites implemented PFS. At least one organization has PFS cipher has preferred for manufacturing, government, and health. PFS not implemented as preferred at all in finance, electronics, and software. So I've been working before into it. I've been working for a financial organization for a while, and my impression was that while they're very good when it comes to privacy rules, when it comes to fraud investigations and things like that, they're not like really good in adopting the latest technologies, the latest standards. So I would not consider them as like real engineering organizations, and probably that's why they just don't pick it up very fast. On the other hand, if we talk about internet companies, which probably are not that good when it comes to privacy, but they are much better when it comes to adopting new technology, including the ones which are related to security. So there is no surprises for me here. Education, universities, this is like the biggest, like most known universities. I'm sure they have a lot of like smart people and very curious people, so they just adopt it because they want to know new stuff. InfoSec defense, in my view, they ought to. They ought to be like at 100%, especially InfoSec world. Many like vendors who are present here have been tested. And having rate at like around 50%, in my view, is not sufficient. They need to do better than that to make sure that they show the case to the rest of the industries and to their clients to make sure that it's possible, it works, and everybody else should follow. So let us take a closer look at internet companies. So this is like when you click on this green bar, this is what you will see. So surprisingly, everybody has agreed to have the same preferred cipher. I don't know why. Probably they have the same consultant working for them, but this is a fact. Just curious one. And then yet another interesting thing, if you compare PFS cipher time, which is the first time column of this table, and compare it with baseline time, then the difference is very insignificant from client point of view, right? So client will not notice. It will not be reflected on response time. We do understand that it might require more CPU time on the server, but it's not visible from client point of view. And finally, protocol support is a little bit of disappointment for me, because they support everything starting from SSL version 3 and ending with TLS version 1.2. In my view, the first two TLS v3, SSL v3 and TLS v1 should not be used anymore because of many security problems. And probably they disabled it after the Spoodle attack, I don't know, SSL v3, but this is how it is. And now let us take a look at red bar, which was found in finance. So you can see like a really gruesome picture in sense of supporting like all the SSL protocols. So the most of them supporting SSL v3 and TLS version 1 only, which are known to be vulnerable, right? Support for PFS is not, so 80% don't support PFS at all, and the rest, 20, don't have PFS as a preferred cipher. So they might support PFS, but it's not a preferred cipher. So in my view, it's a very gruesome picture. It needs to be changed. Especially if you look at this table, which I took from and Qualys community website. They were trying to understand what kind of SSL protocols and what kind of forward secrecy support is available in contemporary browser. And as you can see from this picture, almost like everything is supported. So there are some conclusions that I would like to make out of this. I think there is no any reason why you cannot move your web servers to an application servers to the category 3 and 4, meaning that there is a fallback on non-PFS ciphers, but preferred is still PFS, just like we've seen in like the most popular internet companies. To move it further to level 1 and 2, I think like an executive decision should be made about not supporting legacy browsers. And there are like many reasons why legacy browsers should not be really supported. It's not only about PFS. Even like if you talk to developers, the message from them is very clear. We want to use all latest features of HTML5, and that's why we just don't want to support legacy browsers anymore. And finally, upgrading browsers are usually free, so it doesn't make too much effort or money to move to the newest version. So the conclusion just tells them to upgrade. There is one exception, though. I've talked to a vendor who is in the business of 24/7 network traffic monitoring lately. And we started talking about monitoring our internal traffic. And I told him, you know what, we want to do end-to-end encryption, even if it's data transition, even if it's inside our internal data center or inside our cloud VPC. He said, okay, I can accommodate. Just give me all these private key, long-term keys from your SSL termination point. I put them to this network traffic analyzer, and I will be able to decrypt your traffic. I said, okay, and like, what if like we are using PFS? And then he started scratching his head. Oh, if it's PFS, I cannot do that. Okay, so I think this is like a reason why you might want to have this kind of compromise inside of your internal data center. So you might want to disable PFS for internal traffic, but external traffic will still be PFS. And finally, as promised, here is my vision of perfection in the world of TLS handshake. So you really should have only one algorithm, which is called ECDHE, and most importantly, no fallback on anything less perfect than that. Okay, that's it. Thank you for coming, everyone. I hope I entertained you a little bit.
We have 2 minutes
Yeah, like if you have any questions, like you can either ask now, or like you can use my Twitter moniker and send it to me.
We have 6 minutes for questions.
Yeah, okay.
Anyone has a question? No? In that case, I have a question.
Sure.
So in one of your slides,
Which one?
the earlier slide, you don't need to move to the side. You use the PCP button on your router, remember?
Oh.
Earlier slide.
Yeah. Well, this one.
Yeah, for PCP button, if it's TLS, and you can't see it.
No, you can. This is like my point. You're just like taking this traffic encrypted,
Yeah.
and you store it in encrypted form in Amazon Glacier until this happens. At which time, like you can get this actually like private key and start decrypting. So like I'm storing it encrypted. Yeah. Of course, yes.
Another question is in your cheat sheet.
Okay.
Yeah.
Sure.
Yes, in your cheat sheet. Maybe I understand wrong. For the you have the column you said authentication only, the long-term PDL.
So this means that like actually like in EC, in all the Diffie-Hellman and in CDHE, a long-term key is not used to encrypt your session data. No. It's used only to sign the message. So the attack vector here like a little bit different. If somebody stolen this kind of key, what can happen, he can take this key and set up his own malicious server and try to trick users to connect to it. So this is the only thing. But he will not be able to use this key to the data that has been encrypted before.
It's the long-term keys.
Yeah. No. Yeah. I'm talking about long-term keys.
Okay. All right. Any question?
One question. You said we can't monitor external traffic, right? So what are your suggestions for monitoring the external traffic that is encrypted using PFS?
Yeah, so like you can't actually. You can't. So because like you need to terminate it somehow before you can start monitoring, right? Otherwise it's like will be encrypted, you're not going to see it.
Do you have any other suggestions, like any other technologies that can monitor that kind of traffic?
I don't know. Again, like I do not consider myself like a specialist in this IDS system. That's why like I'm trying to hire somebody to do that. And when I start talking to them, this PFS issue popped up, and he told me, okay, like if you have non-PFS, we can decrypt using your long-term keys. If it's PFS, you're out of line. So I don't know anything else.
Do you hypothesize that we could cut down on identity theft significantly by improving the current state of finance?
Yeah, like identity theft, like in my view, is not like purely a security issue, right? So there's like a lot of factors that can contribute to it, right? Security is one. Security and data protection is one of them. So like if you improve your overall data protection policies and mechanisms, then yes, you can mitigate identity theft as well. So there is like nothing like any specific in PFS that would talk about identity theft. It's just like about data protecting in transit. But data protection in transit is important to prevent identity theft.
All right, let's thank our speaker again.
Okay, thank you. Thank you.